Welcome everyone to the National Road Research Alliance, NRRA 2026 Pavement Conference. We're glad everyone's here and we're really looking forward to being able to share the great innovations and work that's being done. I'd like to encourage everyone to take advantage also of the networking opportunities with the conference participants. Also be sure to check out the student posters just outside these doors. So it's a great opportunity to catch up with people you know, hopefully meet some new people and share some ideas. So one of my specific asks will be, we have construction next year, so definitely want hopefully conversations on what we're going to be doing next year. If you have ideas, thoughts, so try to have some discussions on those. To astute observers in the room, you'll notice I am not Ben Bora, I'm Mark Watson. So unfortunately, Ben is out on medical leave and he's unable to be here physically. He is joining us virtually. Ben did provide permission to share that he's okay. The doctor just wants him to rest and recover from his shoulder surgery. So he'll be back with us before we know it. So first, just want to go over a few housekeeping items. Exits are marked in all four corners here. We do have lunch will be in the same place you got breakfast. We'll enter over here and kind of exit out the back. So we'll have a one-way traffic flow there. Bathrooms, I found them out just outside these doors are the bathrooms. There's also lots of couple nice areas to be able to kind of do some work and have some meetings and connect just outside these doors as well. Recapping the agenda quick, we're going to be in Shoreview for a day and a half, followed by a tour at the Main Road facility where we'll learn more about that tour from Michael tomorrow. I am supposed to remind everyone that there is some walking involved if you plan to go on the tour, so up to 2 miles. So make sure you wear comfortable shoes if you plan on going on that walking tour. Today we'll get an opportunity to hear from all 5 of our teams on their current activities on a wide range of topics. So I'd like to just take a minute here to recognize and thank our leaders on the teams. Starting with Intelligent Construction Technologies of Mike Johnson, who's assumed the chair responsibility after Kyle accepted a new position. Tom Burnham with the Rigid team. Tyler Hunt with the Preventative Maintenance team. Lauren Dow with Outreach and helping do a lot of behind the scenes work and put this conference together. Raul Velasquez with the Geotechnical team. And Kurt Dunn with the Flexible team. With that, I'd like to transition to the 2026 Jerry Rohrbach Award. Jerry was a prominent figure at MnDOT who held a number of positions, including Director of the MnDOT Office of Materials and Road Research, Pavement Design, and others. He was influential both professionally and personally with those he came in contact with, including many in this room. John Garrity was voted on by his peers, and there's a lot of information in your conference handout that goes into a lot of details about John. I'm not going to go through all that. I'm going to try and hit on a few highlights. John really helped make bituminous what it is today in Minnesota. He's guided the state DOT through a number of important changes, including the implementation of SuperPave, bituminous ride specifications, the quality management or QC/QA process that we now use, and many other changes. John is a trusted and recognized expert both within MnDOT and the broader asphalt community. Not only is John a talented engineer, to those who know him, he brings a lot of humor into the workplace. John is also a personal friend of mine who's helped guide me and shape me, and I know many others in the department. So John, if you could please come up to accept your award.
Okay, thanks, Mark, and good morning, everybody. First of all, I'd just like to thank everyone for voting this year. I'm humbled and honored and very happy to be a Jerry Rohrbach recipient. I actually had the opportunity to work for Jerry when he was both pavement design engineer and also as he was director of the building, the Maplewood Lab, where I currently work. But Jerry gave me one piece of advice that I try and follow throughout my career. It's do the best you can and have a lot of fun. And that's what I've been trying to do for the last 37 years. So thank you again. I'm honored for the award. Thanks.
Next up, we have the Gene Skok Scholarship Award. Gene was involved in the pavement industry for more than 50 years, including as a researcher on the original Asheville Road test. And he has worked with several influential companies and organizations, including the Minnesota Highway Department, the precursor to current MnDOT, the Asphalt Institute, Midwest Pavement Technologies, which he started, Ron Intertech, and the Minnesota Asphalt Paving Association. Skok influenced many in the field through his 20 years of teaching at the university. He's also had an impact and influence on many in this room as well. I know it's finals week, so they probably aren't here, but if Connor Hall or Levi Houck are in the room, would you please stand up? Okay. Connor is a senior working on designing a conceptual airport layout and roadway section. He has an interest in transportation engineering. Levi is a sophomore who's currently working as a research assistant at the university's transit lab and will be a transportation intern at Osborne Engineering. He's also one of the captains of the university's concrete canoe team. Please help me congratulate Connor and Levi. Finally, we have the Gene Skok Award presentation. This award recognizes people who've had national and wide-ranging impacts on the field of pavement engineering. Dr. George Chang certainly fits this bill, as he's contributed immensely to the development of modern pavement monitoring, evaluation, and intelligent construction. Dr. Chang is an internationally renowned expert on pavement smoothness. He's the author of ProVal, the primary ride software developed for FHWA. George is also one of the foremost leaders of intelligent construction technologies. He founded the International Society for Intelligent Construction, and he is the author of many of the software currently used for intelligent construction. Dr. Chang's research, teaching, specification development, and software tools have helped make significant technological advancements in transportation engineering. Dr. Chang's presentations and workshops are usually very lively, energetic, and resourceful. He also wields a very contagious positive attitude. Dr. Chang, if you could please come up to receive your award.
Ronan is loading up. Howdy, and good morning. But Glenn this morning asked me, so George, where do you live? Austin, Texas. That's where I've been living, sleeping during the weekend, traveling during the week in the past about 30 years. Thank you. Great. So thank you again. I just talked to Rebecca. I feel like an Oscar night that's here. It's Oscar of Minnesota. I've been working with MnDOT for about 20 years now on a lot of journey. And today I really have to share a journey of passion on pavement that I've been doing for the past 40 years. Oh, I do this. So firstly, I have to thank MnDOT and also NRRA. We've been working as a partner for many, many years. I also would like to acknowledge to all my nominators, colleagues, and collaborators across the agency and the industry. Today, I would like to share my passion over the years on the very different things. So my path, originally back in year 2000, I started the version 1 of ProVal for pavement profile and analysis software, and then later on in the mid 2000 into intelligent construction, and then so talked about Veda, talked about ProVal, and also another software we have released 2 years ago to move from just smoothness to a 3D surfaces for distresses. That's kind of, and definitely I would like to talk about our organization, International Society of Intelligent Construction, and all the standards that we've been impacted on from this organization. and talk about what's next in the future. So here is kind of condensed the 3 decades, what I've been doing on pavement smoothness, intelligent construction, and I've been doing quite not only Veda profile, but several almost 100 different research projects around the country. And Mark just mentioned about, I talked about a lot of workshop on profile smoothness and also intelligent construction. I tried to count how many people I've trained, probably 5,000 engineers each, so about 10,000 people that I've been trained over the years. So intelligent construction journey. Early days, actually, Minda is the one who started the journey of intelligent compaction back in early 2000, about 2000, when John started the IC open house, and that the rest of history. Federal Highway took over, and we got involved, and Minda got involved, NRRA got involved to push the technology over the entire nations. And in the early days, in the mid 2000s, when we started intelligent compaction implementation, there's so many vendors, so many data to manage. So we created a software called Veda to manage and to help to implement intelligent compaction, and later on extended to intelligent construction, easier for the DOTs and the industry. And so here's kind of a timeline of what the various different research effort, pool fund study, and also the research study from NCHRP pool fund over the years in 2004. 2004 is when Federal Highway had published so-called the Intelligent Compaction Roadmap. Bob Horan is one of the authors from Oswald Institute, which is mentioned about that with Dave Johnson on the way here. A lot of journey with Bob Horan, who wrote this IC roadmap. The rest of history, you can see a lot of investment. People ask me when I travel around the world to preach intelligent compaction, they ask how and why the U.S. kind of leading the implementation of intelligent compaction as well as intelligent construction. It's all because there's so many investment in research and collaboration from state DOT, Federal Highway, and pool fund study. I think that two critical involvement that I have here is 2013. That's when we started the Veda desktop software. And then 2022, that's when we converted everything to the cloud. And that's going to be the future and help the implementation of intelligent construction. So the journey is from, we started with intelligent compaction, later kind of evolved to get jointly to leverage other intelligent construction technology, such as PMTP, that kind of mouthful, paver mounted thermal profiling to detect potential thermal segregation behind the screen or paver, and DPS, the dielectric profiling system, which is taken on by another pool fund study. And later on, Minda had led, or Rebecca had led, the development of the AASHTO standard, MDMS, material delivery management system, that expanded the e-ticketing to the whole 9 yards from source, from loading and delivery event, and also the entire agency acceptance on all that. So that kind of a closed loop for the entire construction workflow, from where the material being produced, delivered, dumped, paved, compacted, and accepted. So those technology that we're talking about, IC, PMTP, DPS, and MDMS, that all comply with the AASHTO standard that help not only for here in Minnesota to lead the nation to implement those technology, but also help all other 49 states to implement it by following the national standard. So that's kind of what the journey and what the principle vision is all about. And here kind of show what we started the VEDA with intelligent compaction data management, expanded later on to PMTP for thermal profiling, and then later on to include the DPS for dielectric profiling system. For those who are not familiar with it, it measured the dielectric constant of the top layer of asphalt after paving, and that can be correlated to density. Somebody called it rolling density meter, but the raw measurements is DPS. Like I said, it closed the loop for the entire paving flow. And we work very closely with NRRA. That's Dick, Glenn, and I, when we joined as a partner. It's all about partnership. It takes a village to really move forward this technology. And that's a fun fact, though. Glenn, do you remember 2012 at TRV? So Glenn said, I'm thirsty. Okay, let's have a beer. So we went to a Irish bar at the DC Marriott, and then we talked about compaction, intelligent compaction. So I flipped open my laptop and showed Glenn the prototype of VEDA software. And Glenn said, that's what we want. So that's the beginning of VEDA, and the rest is history. Thank you, Glenn. And another hat that I have is smoothness. So back in 2026 years ago, some of you probably somewhere. Anyway, so the year 2000, that's when Federal Highway, I think Tom used here from Federal Highway. Federal Highway have this vision that can we standardize pavement smoothness? There are dozens and dozens of different vendors collecting pavement smoothness data, but reporting different metrics, different data format. Can we have a standard way to do it? So that's when Mark Swanman and us started to put together a software called Profile, which is profile viewing and analysis of software to standardize the software to import all the different pavement smoothness data into a standard software, and then have a standard reporting, very robust, traceable result that all state can be taken to use in their smoothness spec for construction acceptance. And that title pay items, incentive and disincentive. And so that's a start in year 2000 when we released 1.0 Profile. Later, for the past 26 years, we listened to users like you and improve and enhance Profile over years. And now it's Profile 4.0. And then 2 years ago, we also extended the 2D, which is pavement smoothness, application to 3D, which is pavement surface, 3D scanning, LiDAR type of data standardization, similar to the route to standardize pavement smoothness. And this so-called Clarity as another software to standardize the 3D surface data, which is also follow AASHTO standard, and to enable all 50 states to implement any of the 3D technology to be able to standardize it, and also can perform a quality assurance by viewing the data, validate the data. So that's the purpose of the Clarity. And here's the brief history of pavement profiling, all the way traced back to 1950s when we started with the rolling straight edge, and then later on to a response system for measuring pavement smoothness, and later on to so-called the inertial profiling system, which is high-speed version being used today. And later on, since year 2000, 2010, and the technology started to evolve into a 3D surface. And eventually, this technology may be all going to converge. And so Profile, and in this case, is emerged in 2000, and then be involved along with the support and sponsorship from another pool fund study, which I'm going to tonight at ARPA conference for that. So that's a 26 years of journey to help the nation to all 50 states to standardize profile viewing, analysis, and reporting, and implement the IRI standard-based standard, the International Roughness Index standard, by converting from the old profile graph index base to the IRI. So the nations can have a standardized way to evaluate smoothness and report it to the federal highway HPMS system with a standard and robust reporting system. So this profile is, like I said, is a standard platform for any profiling system to import the data in. So this can do, it's a global tool. It's R56. So that's what we're going to talk about a lot at the ARPA conference in the next few days in Pittsburgh, Pennsylvania, is to ensure all profiling system and their operator are properly certified before they can collect reliable, robust, and correct data for pavement construction acceptance. So that's our AASHTO R56 certification all about. And R56 now have been evolved to our so-called stop and go and low speed profiling system that can collect data of smoothness data reliably, even with a low speed section of highway or city area or any places that may have a stop and go due to this traffic light or a railroad crossing anyway. So those are the ones that have been evolving, and from federal higher research to this free, again, Veda and Profile software has been free because it's been standardized and sponsored by the pool fund study and always comply with the AASHTO standard. So it's not only for standardization for construction acceptance, but also for state DOTs, quality assurance for any state that allow the contractor to collect the pavement smoothness data. Profile will allow them to do a standardized quality assurance data to compare a portion of up to 20% of the contractor data with the state-owned or certified standard profiling the data, so they can compare, and then using the quality assurance ensure that contract data is correct and for the acceptance. And forensic has been used a lot for a lot of study using Prova and also all kind of spin. So Prova is not just a reporting software. It also includes a lot of modules. So whenever I taught Prova workshop, it was typically a one-day workshop, and people just surprised that it's not just feeding the data from profile and then spit out IRI and done with it. If it's so, then profile is not won't be like profile today. It's a standard platform, have a lot of important module that help to improve payment smoothness. So it's not just standard reporting, but help the contractor and inspector DOTs to improve the payment smoothness. Use all kinds of different modules to inspect, evaluate the paving issues, paving problems, and find a solution to resolve. Like I said, all the things I've been doing over my career is all comply with the AASHTO standard and also ASTM standard. I'm involved in the ASTM E17 committee to standardize as much as possible for payment smoothness and also data format, as well as other weight in motion and other faulting and also certification module. Those are kind of a mirror and counterpart of the AASHTO standard. So I've been working very closely with the AASHTO as well as the ASTM standard to make sure they're all compatible or in line with each other. So for those of you that don't know, AASHTO standard serve for all 50 states, and ASTM, they call ASTM International Standard, they serve not only the US, but also the rest of the world. So we're serving and helping the world to implement those technology also. So I started with a 2D pavement smoothness in year 2000. In the past decade also, the technology has evolved to using a 3D LiDAR system to scan the entire pavement surface to be able to gather the correct exist or current pavement surface data and use those high quality data. So those data are not simply just color or images. These are including the intensity data, which is show the intensity, kind of like the black and white photo of pavement surface data, as well as the elevation data, which is surface data. So combining these two data is the current so-called high-speed 2D, 3D surface data being collected by those technologies, notably pathway or pavement system around the country. Just like the similar needs to standardize pavement smoothness, now the clarity software that the pool fund study for the districts pool fund that help work with us to develop this clarity is to standardize such a software to be able to view it, because to analyze it, so it can be standardized and easier for DOT to implement around the country. So what this can do, not only validate the data, but also can bring in rotting picture, surface, cracking standard in the future. Currently, it's doing rotting only, but in the future, it can be used by DOT to verify the contractor's data collecting for your highway system for rotting, cracking using this kind of software. So switch down to ISIC. People always said, well, it's ISIC? No, it's ISIC, International Society for Intelligent Construction. This been it's been taught for years, but in year 2000, one of the collaborator, co-founder is here, Dr. Sohail Nazarian. We co-founded in 2016. Now we have 500 something members, and we conduct a conference every 2 years. And we also have a lot of workshops and webinar being conducted. And so this International Society for Intelligent Construction is create a global platform for all the expert producer and users of intelligent construction technology to share experience, technology, hurdles, solutions for any of the subdomain technologies such as sensing technology, data analysis, including data standardization, decision making, also the highway asset cycles. And we also have produced or written, we've been busy writing over the weekend at nighttime, a lot of textbooks for university or any agency training program to train the current generation and the future workforce to be able to handle and manage the intelligent construction technology. So these are 4 founders. So here's here. Thank you, Sohail. And Antonio from Portugal, and also Professor Xu from China. 4 of us were founded. I have more hair than. So it's our 10 years anniversary. So we're celebrating 10th anniversary this year. We're also celebrating 50th anniversary of Intelligent Compassion this year. We've been written several dozens of articles and posted on our website pretty much every week throughout the year to celebrate the 50th anniversary of Intelligent Compassion. And we have a lot of members, and some of them are from NRRA, including Kurt, Rebecca, Todd is here, Amanda's here, Tim have missing, Lars missing, Kevin from and Jim. So here's our powerful and cohesive North American chapter officer that have been working together. Dave is here, most of our members are here, that have been working very closely. They're meeting every couple of weeks to really help to organize a streamlined effort for helping all 50 states to implement intelligent construction technologies. And we are having a conference in August. I'm going to show you more detail later to continue this effort. There will be a 3-day conference there in Louisville, Kentucky. So we have done quite a bit of training. How many minutes I have, Lord? Okay. So we have a lot of training. Matt just showed me the poll. I don't want to steal his thunder here. We have survey around the country over the years. The biggest hurdle, biggest needs for implementing intelligent construction technology is training. So did a lot of training, education, and also publish a lot of article and books to help to do the training. So we have a lot of training program, not only the training through tech lecture, but also hands-on with VEDA software, and oftentimes we'll also combine with the equipment demo, so people can kick the tire, kick the drum, roll the drum, and they see for themselves. So those are combination lecture, hands-on with software, and also equipment demo, and sometimes field demo really help to educate people to know about intelligent construction technology. So we've been debating this forever, even among ourselves at ISIC. What would be the way to kickstart and make, just let the ISIC intelligent construction technology to run its course? You have to start with the top down. You have to start with the specification. Vendor always said, well, they've been selling this to a contractor. They all like it, but DOT, like you have to specify it. You have to require it. Then you will start the journey from specification, from a pilot to a full scale, and then equipment supplier will invest, and technical support will run back. And then the technology transfer and training will be needed to move it to the next step. And then when the DOT and contractors start collect so much data, then you have to have a data management program to kind of streamline the step-by-step journey to implement the intelligent construction technology. So the standard adoption is very important. So we're always pushing the standard, and always, so that standard will help to consistently, reliably, to ensure we use the technology to improve the paving construction quality and performance assessment. So what's next? We're working hard, actually. Well, I'm having fun here, but all our workers are working very hard back end to improve, to move the VEDA software to a cloud base, including several modules and DMS for material delivery system, and they're implementing the rest of the VEDA desktop feature to the cloud as we speak, including intelligent compaction, multi-thermal profiling, and dielectric profiling system. And somebody always asks, will AI and machine learning be included? Yes, it will be in the future. It's on the wish list, and Rebecca's here. Probably can tell you more about that. Minda already have prototype on that, so that eventually that will be included. This new cloud-based VEDA is called VEDA Center that will include everything. Also, AASHTO standard for so-called API, application programming interface, to work with all different vendors to standardize it, and so connect everything, because it's a web-based from the field, from the lab, from design, and pretty much in real time. So those are standard we're going to do, and here's the VEDA Center that will include everything and merge and fuse all the data together from the entire paving train, and desktop in several months will be all on the web. So that's a full module I mentioned about. And this is Hope y'all can attend our ISIC North American Conference in Louisville from August 24 to 26. So we can talk more about intelligent construction technology. So this is my brief journey of my 30 years of smoothness, intelligent construction, and thank you so much.
Right, good morning, everyone. Hope you're gonna enjoy the program that the NRRA Geotech team put together. Hoping that you're gonna get a few items that you can bring to put it in your toolbox as an engineer. And further ado, I'm just gonna briefly introduce Silas, the first speaker. You can read his bio in the program. But I'm very thankful to have him coming to speak to you guys. He doesn't usually speak to pavement folk like you. So he's gonna come and tell you a little bit about strategic goals, related to transportation geotechnics. And really, I just want again to thank you for coming all the way from DC to talk to you guys. I can tell you from a personal perspective that you are very influential. You have a lot of knowledge and you are key for the community, for the geotech community, especially during these critical times or these very challenging times. I really appreciate your leadership, that you stick to it, and you're still working for us and helping us out, not just the Midwest geotech, but other geotechs. Thank you very much, Silas, for coming.
Good morning, and I'd like to open by saying I love pavement engineers, despite what you just heard. So for those of you who don't know me, I'm the principal geotechnical engineer for the Federal Highway Administration, and I do sit in Washington, D.C. And this is not going to be a pavements talk. As you probably are aware, we in the federal government are restructuring a little bit based on some events over the last year. My group is restructuring probably as much as anybody's as we lost a lot of stuff. And so we are reorganizing and sort of putting everything together. And so what this is today is sort of a look at what our strategic vision is going forward. And for some of you who've seen parts of it before, you will see some things familiar because we're trying hard not to change too much. We're just trying to figure out how we're going to do what we need to do in the future to best help state departments of transportation and our transportation partners. And so off the bat, we have disclaimers. Don't try and read all that. That just tells you don't sue me later or don't sue us later or don't say anything bad about this later. Okay, so the FHWA Geotechnical program. I think the most significant thing that happened to federal highways over the last year is that our resource center no longer exists. So the group of people that were designed to provide technical assistance to state departments of transportation, work on deployment, implementation, training needs, things like that, has been collapsed into our headquarters office. And now it resides with my office, so to speak. And so with that, we've had to sort of look at a difference in what our roles and responsibilities are going to be here at Federal Highways in the headquarters office. And headquarters now will pretty much contain just about everything we do on the federal aid side, including research, which has always been a part of headquarters, though nobody really thought about it as a headquarters function. But with our roles and responsibilities, we'll continue to provide direct support of state project delivery and review critical and complex structures, which we've been doing nonstop. We are continuing to develop and provide information and assist in the development and maintenance of guidance and state manuals and things like that. We are still in the business of research identification, support, and actually conducting of, and we still have a National Highway Institute curriculum and a training program for which we're providing oversight to. We are trying to grow it. I'll get to that a little bit later, but the idea is that a lot of our communication is going to start to move over to NHI in ways that we haven't really thought about it before. With regard to our strategic plan, we do still maintain roadmaps, both in our research office. So Jennifer Nix manages and runs our geotechnical laboratories, our geotechnical research program. She maintains one of our roadmaps. I maintain the other one on the program office and development side. It is a series of broad concepts where we plan to put our money in the very near future. So it reflects trends and opportunities influencing and impacting the discipline, some of our priorities for spending through our annual geotechnical plans. And it is informed by a lot of different entities, including states and academia and industry, et cetera. The way that we are currently influenced hasn't really changed over the last couple of years. Our big amplifying problems still are our big amplifying problems. And so we've got this issue of construction means and methods sort of driving a lot of the things that we do on the geotechnical side of the house. So I spend most of my time in structure development, bridges, walls, et cetera. And over there, probably our biggest issue is the fact that the construction industry has figured out how to make things ever bigger, ever deeper. If you are familiar with deep foundation design and construction, if I told you that we are now routinely on the West Coast doing drilled shafts that are in excess of 10 and 12 feet in diameter and approaching 200 to 250 feet in depth, you'd probably shake your head a little bit and say, wow, that's bigger than things that we should be building. And it is. And we have to figure out ways to sort of govern that. Even on the driven side, we are now routinely driving piles that are 6 and 8 feet in diameter. And in fact, the Key Bridge, which is in the news this morning because apparently we lost the contractor on it. I learn more about that this afternoon. But they're driving 8-foot diameter pipe piles out there right now. We're having problems with them because they're 8-foot diameter pipe piles. It's difficult to do these things, and that has been a constant problem. We're continuing to have issues with the application of load and resistance factor design and geotechnical applications specifically, and an understanding of what geotechnical strength limit state really means. Does geotechnical strength really belong to the foundation, or does it belong to the structure? And we're trying to identify ways to actually deal with that problem. We're trying to understand the risks associated with characterizing geohazards. And really what that is a better understanding of how we're thinking about preliminary engineering. I hopefully scared Derek Dassenbrock a little bit yesterday afternoon when I sent him a note and said, I'm coming to Minnesota and I want to spend a lot of time with you talking about data. And he said, data. And really what I wanted to talk to him about was how we're going to do a better job of characterizing sites up front so that we can get into designs a little bit more efficiently and process workflow a little bit better. This is also a pavements problem where we spend a lot of time looking for ways to handle long linear infrastructure through a series of discrete holes in the ground and then some assessment through geophysics or other means of what all of that means when you try to tie it all together. And as all of you know, it is very difficult to get a consistent look at what the subgrade looks like, what a pavement box looks like with depth, and to do that with some level of reliability. And it is a problem for all of geotechnical engineering as well. Larry Olson, who's sitting in the back there, is a long time friend. When I first started doing my PhD work in 1995 or 6 or something like that. He was one of the very first people I met because he was essentially developing what became what we look at as tomography today around some of the research I was doing out in Denver. And so we were standing out in the fields in North Colorado for days at a time in hot summer heat. And we've been friends ever since. It's nice. The last thing we have is cross-discipline cooperation. The more and more we continue to grow and evolve, the more and more we become reliant on other disciplines for understanding how they work in order to make our work better. That includes pavements and structures and hydraulics and some of the others. So when everything is said and done, for the last several years, we've had 5 major pots where we have been sort of assigning money for research purposes, for development purposes. Innovations in geotechnical design and construction methods is just that. It is the evolution of construction means and methods and the size of elements and our ability to try and govern all of these new construction means and methods and innovative construction means and methods. Advanced site characterization points back to that whole geohazard issue and doing a better and more reliable job of understanding the input parameters to design so that we can do a better job of delivering projects. Asset management and performance management. That really looks at our ability to understand long-term in-service performance of geotechnical assets, including pavement subgrades, which is nearly impossible because you can't see them or touch them. And so how do we know, for instance, if we are doing something below ground and then covering up with pavement for 75 years, how we're getting performance out of that long term. We really don't. We're looking for ways to try and better understand that. Geotechnics of Scour. Jennifer Nix has been working on some really impressive work lately, looking at scour and clays. We are trying to get some stuff published. I'll talk about a couple slides, but very, very impressive work. And then finally, our geotechnical aspects of pavements, understanding that pavements are our single largest asset in a DOT, and the fact that we really have been disconnected as a geotechnical program from our pavements program. We have been working with the pavements group and some external partners to see if we can't do a better job of integrating with our pavements group to look at such things as permanent foundations under pavements as a concept. So what does that mean in terms of a long-term strategic vision? Well, I would argue, and I have been trying to argue over the last few days, that my life has been consumed in just a couple of big picture areas. And really what that is understanding remaining service life of just about everything, but mostly structure foundations. Because if we can't understand what our reliability is in the ground, we can't do a lot of other things. And that specifically relates to such things as reuse of foundations. So just coincidentally, the photo on the page is a bridge on 8th Street Northeast in Washington, D.C. It's about a half a mile from my house. It runs right behind Union Station, which is where the picture is being taken from, and it looks west toward downtown. And the thing you might note is that there isn't a lot of space on either side of that bridge. In fact, if you actually went out there and looked at it closer, you'd find that it was less than a foot to the buildings on some spaces. It's in there very tight. So the bridge was built first, we put buildings around it. And as you might guess, a bridge does not have an infinite life. And so we are in the process right this second of trying to figure out how to replace this bridge in service. So we can't really take it out. We're going to have to keep traffic on it, but we have to figure out how to replace the bridge. So redecking it is easy, right? We do that all of the time. But what do we do with the substructures and the foundations underneath this to try and assure that we can get another 75 to 100 to 125 years of life out of this bridge when you can't actually get to the substructures and the foundations, right? Oh, by the way, we cross over Amtrak tax here. So any of you who deal with trains know how difficult that is also. And so we are looking at a lot of different ways of understanding remaining service life, understanding reuse and foundations, and how we would get to reuse, and understanding when we can't reuse or when it is ineffective to reuse, how to enhance. I don't know who needs to know this, but your battery's dying up here. Got it. Where was I? Yes. And looking at ways to structurally enhance foundations when we can't actually reuse things. So figuring out ways to understand what is left below ground and how to enhance that to then extend service life of the structure. So there's a lot going on here. Resilience and adaptation strategies for geotechnical features and elements. This looks at a lot of our hazard, and I'm not supposed to say the words, but I'm going to say them anyway, climate change issues associated with maintaining our right-of-ways, right? We go out into roads anywhere in the country and we look up at slopes, and how do you know whether or not a slope is performing well or not performing well? Well, we really don't, because geotechnically we grade just about everything on a pass-fail curve. Pavements generally have a deterioration model. We can go out, we can look at such things as cracking and rutting and other things to make some assessment of how a roadway or how a pavement structure is performing over time. And we can make adjustments or adapt to what is going on in that roadway in real time. With a slope, it is either there or it is not there. With a wall, it is generally the same. We can see it leaning, but generally it is there and then it is not there. And what we don't really have at the moment are ways to think about resilience in a responsible and proactive way, or think about adaptation for these features in a way that allows us to treat things along the way based on how they're being affected in long-term performance. So the long-term strategic vision for us really revolves around our ability to do something that we hadn't really thought about before, which is we're at the end of life and we're not going to be able to replace everything. That's just not financially possible. So how do we get more out of it? And how geotechnically can we assure ourselves of a level of reliability that allows us to do that? So, I'll start with a couple of things that we are currently working on, with that as sort of the background. One of the first things that we are working on actually started about 15 years ago when we started to write an update to our GEC 5 document, Geotechnical Engineering Circular 5, on soil and rock properties. We ended up titling the new document Site Characterization. And the idea was pretty simple. If we look at geotechnical design across the board, we generally accept the fact that we are going to have changes in just about everything except soil and rock properties. We don't really think about the input parameters as well as we probably should. And so we went back when we were writing this and we started thinking about what uncertainty in a geotechnical design parameter should look like and how should we be able to assess that going forward. So it should make sense to you that if I were developing the exact same project on a homogeneous site versus a heterogeneous site, the way that we think about what the design parameters are going to be very, very different, right? The reliability of sand, just sand to 150 feet is one thing with respect to how I think about characterizing the site. A very, very loud glacial till that's bouldery, clay seams, sand seams is going to look a little bit different when I do the same exact thing with a code. But a code doesn't really acknowledge that. A code just gives you a sort of minimum standard of care of do a boring here, take a couple samples, move on. And we don't really address uncertainty in the site characterization process very well. And so when we sat down to write GEC 5, that was the plan, to think about a way to address uncertainty in site characterization in a way that made it a little bit more reliable for delivering projects. AASHTO came along the last couple of years, and for those of you who work at state DOTs, you've seen this. For those of you who just attend a bunch of conferences, you've heard a lot of different people talking about the fact that we are rewriting Section 10 right now in the AASHTO Bridge Design Specifications. And this will trickle out to other areas. This, I think, is going to be sort of a seminal change in the way that we think about preliminary engineering. But the Soil Structure Committee at AASHTO has gone through, and we have finally submitted the ballot item this year to be voted on. For those who need to know, this computer is about to restart. So we finally submitted the ballot item that rewrites all of Section 10. And the idea here is that we haven't really changed the way that we think about construction control for determining reliability and foundations. What we have thought about is the way that we do static analysis and sizing of foundations in general, and how that's going to look in the future with respect to uncertainty as it relates to the site characterization program. And so the primary intent of the update is to address this uncertainty of the site characterization procedures and the reliability of soil rock parameters, termination of foundation design and construction. Now, I have an hour and a half of slides on this if you want them at a later date. I'm not going to give those to you now. I'm just going to tell you the premise. The premise goes like this. If I had enough data that I could do a statistical analysis of that data set as part of project delivery, I should be able to look at how variable that data is and make some assessment about how reliable the design parameter is coming out of the other side, right? And so the idea here is that if I could take a minimum amount of data for any project that I am looking at and look specifically at the most sensitive design parameter in the design model, I could look at the coefficient of variation for that specific item and make a determination as to whether or not I have done enough work in subsurface investigation and in gathering of data to determine whether or not that design parameter meets what is a minimum level of reliability that would be set by LRFD or any other code, right? So for us, we had a research team in from the University of Missouri, led by Eric Lohr with Andy Beckman, who was his chief researcher at the time, working with him. And we were all sitting in a room one day back in like 2014 or something like that. And we were thinking about what the coefficient of variation number should be, and we thought about it a little bit more, We looked at some data, thought about it one more time. And then we just reached up into the air and grabbed 0.3 as the coefficient of variation that we thought was the break line between what is the standard practice today and something that shouldn't be used at all. So we generally are saying to people that if you meet a coefficient of variation of 0.3 with a data set that has been properly obtained, then you are most likely meeting the level of reliability that was intended in all of the calibration of LRFD to begin with, if you use just a minimum standard of care for doing your site characterization program. Okay, so with that, the way the code is going to look in the future, hopefully, if we can get this through Charlotte in June, is that instead of there being a section 10.5 where we had all these resistance factors just sort of tucked into tables, we've now moved all of the resistance factors to match the designed elements that you're working on. So if you go to 10.6, which is the shallow foundations design section, the resistance factors that are specific to shallow foundations are all going to be in 10.6 now, not there. And 10.7 will be driven piles, 10.8 will be drilled shafts, 10.9 will be micropiles. And you will have a table that looks something like this that you can't read, so don't worry about it. But it essentially gives you the static analysis method that you're going to be using to size the foundation. It'll tell you what article you're going to in order to learn how to apply that, or to tell you how to apply that specific model. And then it's going to give you something called a critical design parameter, or the design parameter in the model that is most sensitive to its effectiveness, right? So if you're looking at like a drill shaft side friction design, the critical design parameter would be shear strength of the clay, right? So under those circumstances, that would be the parameter that we are looking at the coefficient of variation for. This does not absolve you from being diligent about all of the other parameters. It just looks at the critical design parameter. The second thing that you will see is that for every one of these models, there will be a chart that looks something like this, where if you are doing more than the minimum standard of care, we think you should be rewarded for that. And so our research teams have gone through and they've sort of looked at what the sensitivity of that coefficient of variation should look like. So some curves are flatter, some curves are steeper, and how that should reflect a level of reliability and how the model is applied, or a resistance factor in this case. And so the two things you'll note are that the coefficient of variation runs against the resistance factor for a specific design parameter on the y-axis. And the second thing you'll notice is that below 0.3, the line is dashed. So one of the things that I think people are mistaking here is that if you are just using the current code today, period, and you are responsible as a design engineer, then you should meet 0.3 as a minimum. What we are doing is rewarding you for doing more. The second sort of big picture item that we are getting involved in hasn't started yet. It should have started in January. We are still waiting on some final pieces of paperwork to start. But we have been given an opportunity by Texas A&M University to go down and deconstruct one of their national geotechnical experimentation sites. So let me back up. Back in the early 1980s, the Federal Highway Administration partnered with the National Science Foundation to fund a series of characterized outdoor laboratories around the country. We built 6 initially as Tier 1 facilities, Tier 1 meaning that they were extremely well characterized. And the idea was that once the labs were built and developed, then we could allow geotechnical contractors, engineers, researchers to go out and use the sites to do experimentation of any kind. So the most famous one was like Treasure Island out in San Francisco. It no longer exists. It was taken out and now there are condos sitting on it. But we had Tier 1 sites around the country at Texas A&M, at the University of Massachusetts, at Northwestern University. I think the one at Auburn University still exists. But they are getting ready to do some construction on one of the sites at Texas A&M. And so they called us up and asked us if we would be interested in coming down and helping them decommission the site. And to us, decommissioning meant a lot. It meant that for a site that was initially characterized back in the mid to late 80s, so the 84 to 88 range. We went out and did all of the work to develop just the laboratory. And then starting in the early 90s through about 5 or 6 years ago, we have just been installing things in the site. Drilled shafts, anchors, soil nails, steel sheet piles, all kinds of different types of elements have been installed in the system over the last 50 years. We are intending to go out and exhume as much stuff as we possibly can. We've got the help of a number of trade associations and a number of outside consultants to just sort of give us guidance on how to do this and then how to proceed with the next steps, which is a long-term research effort to look at the performance of all of these elements from the standpoint of what we knew at the time that we designed and built them. So if you're looking, for instance, at a drilled shaft, we built a bunch of drilled shafts out there with defects in them already, specifically because at that time, we were developing a lot of our geophysical technologies and we were trying to find things. And in this case, we were trying to find defects. And so we've got a bunch of exposed steel at different levels in these sites that we want to be able to see whether or not the way that we think about corrosion as a suite of testing and as a performance item, whether that matches the metrics we're currently using to assess aggressive ground. We want to be able to look at long-term performance of concrete, long-term performance of steel in the ground, and we now have an opportunity to do that. We're going to be developing test methods to look at things that we don't know how to look at right this second. So if you are trying to evaluate aggressive ground, for instance, one of the things that we know is that if you're going to have corrosion, you kind of need oxygen, but nobody knows how to measure oxygen content in soil. And so we're trying to figure out ways to do that. So there'll be test developments going on also. We have a long-standing project going on. It's been going on for several years right now, just looking at the evaluation of geotechnical limit states for structural foundations. And again, the idea here is that as the elements get bigger, they become harder and harder and harder to design and understand. We work in a big strain sort of arena, a load deformation arena. You put load on it, it deforms. We pick some arbitrary location and we call that nominal resistance. So in a 12-foot diameter or 12-inch diameter element, that's fine. In a 12-foot diameter element, that's a lot of movement that can't be tolerated, which gets us back to whether or not geotechnical strength limit state belongs to the geotechnical engineers or not. We are still looking at a lot of different things in there, but I think so far we are understanding a lot more than I thought we would. We are looking at quality assurance procedures for large diameter drilled shafts. The evolution of rotators and oscillators has made it impossible for us to understand some things. Thank you. I want to point out that's 3 pieces of technology that have interrupted this presentation already. Rotators and oscillators that have made our understanding of quality assurance and acceptance in drilled shafts very, very difficult of late. And so we're looking at some changes there. I mentioned Jennifer Nix earlier. She's working on some approaches for looking at allowable critical shear stress in clays. That essentially looks at part of our research strategy for next scour, which is a better understanding of the geotechnical aspects of scour. She's doing some really, really interesting and impressive work there. We have some papers in draft, so you state DOT people who want to get an advanced copy of it, just call us and tell us you want to review it, and we'll send you a copy. Jennifer's listening, and I hope it's okay with her. We have a broad agency announcement, a big research effort in liquefaction hazard assessment going on right now. It is with the UCLA Next Generation Liquefaction Group. We are working with them on models that are going to improve, we hope, the idea of understanding liquefaction triggering, liquefaction susceptibility, and liquefaction manifestation, which is something I don't quite understand, but they tell me that even if it doesn't manifest, you can still tell it liquefied. Fine. We'll see how that goes here in the future, but we are a few tests into that. There are just a few additional activities going on. I won't go into them in real detail, but we've got some external projects, including one that Tom Yu is working on, which is a demonstration project for long life pavement foundation systems. That is a pooled fund that is just getting underway. So find him at lunch and pick his brain about what's going on with that. We've also got some contract former postdoc employees at Turner Fairbank who are working on some roughness measurement devices for gravel roads, think IRI pavements, but for gravel roads, calls it RTK GPS cart, so testing device mounted on a golf cart. So a bunch of things like that are going on, and some other things that we are sort of got on a wish list of things that we want to look at here in the near future. The last thing I'll mention here, like I said, we're going to be doing a lot more work through NHI for communication. So we're going to continue to develop and continue to assess and continue to write and continue to document. But we aren't going to have the resources to really run around the country and do the things that we used to be able to do before, which means that we're going to have to find different ways to communicate with state DOTs and our partners. And so you'll start to see a lot more work through NHI to help us out with communicating results and communicating developments that we're doing both in-house and overseeing externally. And I hope that in the near future that will find its way to be practical and efficient for the way that states continue to deliver projects. So with that, I'll say thank you. That's the I-95 bridge in Philadelphia that burned down a couple of years ago that we rebuilt geotechnically until they could come in with a structural solution. So we were able to get the bridge back open in 3 weeks by using foam glass aggregate fills that just ran 24 hours a day through all kinds of weather until we got up, paved it, put a wall facing on it, reopened it to traffic, and then 6 or 8 weeks later, they finally started getting pieces in for the bridge, and they rebuilt the bridges around it. So, thank you.
Sorry about that. Maybe one question or two for Silas, or maybe after the going break. Any critical question right now? He's going to break. Thank you. Thank you. Next topic, next presentation is an emerging technology that geotechs are very excited about it, and it's the use of satellite technology to track movement of your assets, specifically geotechnical assets. So this is not an NRRA sponsored project. This is actually a project sponsored by MINDA, but we wanted to showcase the current state of technology for this technology, so you get some excitement from membership, especially for DOTs, to see how it's working right now. So, Professor Ali from Auburn graciously came to present this. Sorry, you're gonna have only 15 minutes. Hopefully, you can put the point, deliver the main topics. And their students drove 20 hours from Auburn to bring these equipments, to bring these sensors that we going to be installing across Minnesota to try really to test this technology. So anyway, I'm going to stop talking, let Ali talk the technology, and yeah, hopefully you guys get excited about the inSAR.
That's fine, I'm going to actually go walk. Hi, everyone, and thank you so much for having me and my students. We came here to present a topic, as Raul mentioned, use of satellite imaging and inSAR to measure ground information, mainly for geotechnical asset management. I'm here with my students, so I kind of flew for 2 hours, 30 minutes to get here. My students drove for 20 hours to get here, so we all know the suffers that they had before, right? So there's professors. This is the team that are involved in this research. It's a collaborative work between Auburn University and University of Texas A&M. They have me, Dr. Kupala, and then Dr. Montgomery. We also have a collaborator in the UK, University of Exeter, Dr. Matsuri, with background in inSAR and remote sensing. I also have my students with me today, Najib, Zahra, and Vadova. They are the brain and muscle behind this work. And then they're going to have some posters today. In case you have any questions, follow-up questions regarding this topic, reach out to them and then ask questions. The motivation behind this topic is that, we all know that when in many states in the U.S., especially Midwest, we have ground deformation caused by landslides, sinkholes, or culvert damage, resulting in significant damage to the highway systems, roads, and then transportation infrastructure in general. Preventing these types of deformation is almost impossible. However, accurate and continuous monitoring of this information will allow us to come up with proper measures in that the time of need to prevent significant damage to the highways. Traditionally, monitoring. These types of deformations are used by either surveying, instrumentation, and technologies like that, which provide very good, accurate data. However, they come with limitations. First of all, they provide measurements at very focused locations. They are time consuming, the installations, they need a lot of manpower, and they kind of require considerable resources and effort. And then the main issue is that you can use them only in locations that have already shown some sort of damage or distress. Here we propose an alternative approach. That's the use of satellite imaging, especially interferometric synthetic aperture radar, known as inSAR, that provide a better spatial coverage, global scale almost, and also it has very short revisit periods. It means that it will provide us near continuous monitoring of geotechnical assets. But exactly how this inSAR technique works, here you can see a constellation of two satellites, mainly for one of the systems that is known as Sentinel-1. We have two satellites orbiting the ground along some orbits that is near like polar orbits, and then they have each satellite has a 12-day revisit period, and with two satellites they're going to have it down to 6 days. It means every location on the Earth is going to be visited by the satellite every 6 days. And then so with that you can imagine that we're going to have continuous almost, because 6 days, if you think about it, it's going to be very short, right? The monitoring, so it's kind of providing us with a very near continuous monitoring of the formation. There are always, some confusion about what SAR, what inSAR is. So while these satellites were reading the Earth, they take images. They were reading south to north, as you saw in the image, but they're looking sideways and they take images. What they'll do that. The image that we got from these satellites is what we call SAR image. It's 1D, and it's usually happen along the direction of the look of the satellite. That's what we call LOS, or line of sight. These images at the beginning, when you look at them, looks like some normal image, but then it's more complicated than it provides you more information. It's like a complex number. It has two parts. It has a real part, which we call amplitude, and it has an imaginary part, which we call phase. Amplitude is pretty much like normal images of aerial photograph that you see. But then phase is like, some random pixels with different colors. And each color, when it's brightest, means, better quality. When it's faded, it's low quality. And then when we go to the wavelengths domain, amplitude is pretty much the length, the height of the wave. And then when we talk about phase, it's almost where we are in this wavelengths. And the value is going to change from 0 to 2 pi. If we ignore the amplitude at this moment, focus only on phase, you can see that's it's just some random pixels, right? Numbers of pixels, and it doesn't give us anything. But the magic happens when we combine more than one photo in our analysis. Imagine that we have image 1, image A from some period of time, and then image B taken some days after. This one is for 25, 26 days after the first image. If we ignore amplitude and just focus on the phase, we can subtract phase from image A and image B and come up with a new image that we call interferogram. And that interferogram is what provides us with the deformation pattern in the region. This process, taking images, getting to interferogram, is what we call interferometric SAR or inSAR. So that's the difference. In general, when we talk about SAR, it's more mainly the image, the data we get. When we talk about inSAR, it's the process, the technology, the technique that we get to interferogram. This cartoon shows the whole process in a simpler way. So imagine that we have these satellites. These satellites have SAR sensors, and SAR sensors are pretty much like a microwave sensor. They send waves to the ground, and they receive the backscatter. And then with that, we know the length of the wave, but how many of these waves we have, we don't know, because the distance is known, but then still we need many of them. And then it's like, having a ruler that has multiple ticks. We know what's the distance, but we know how many of them we have. Now think about this satellite taking one wave in a certain time. and then it come back later and taking another wave, and then get some scattered data from that wave. And then we start comparing these two wavelengths together. If the satellite visit comes and shows no difference in the wavelengths that we got from first and the second image, means the ground hasn't moved at all. But if you see a difference, that difference is resulted from some sort of deformation that we have in the ground. So it's pretty much like that. And then that tells us, that phase difference is what we call inSAR. The phase measurements that we get from this technique usually comes with multiple terms. As you can see, 5. We have some phase difference due to geometric effect, which is mostly about Earth's curvature. We have it due to topography. We have it due to atmospheric, and then we have it from some noises that we have in the region. So at the end, we have the phase difference due to deformation. So there are techniques that we can measure the first 4 components of this equation. We have that the first measurement on the left side of the equation from satellites. The other 4, we have it from some technology, some techniques that presented in literature. So from these, we can easily get the deformation, the phase difference due to deformation. When we have these satellites, they usually look at the Earth from 2 different angles. As I said, they're usually already in the ground, south-north. But the satellite right here, for example, this is for Sentinel-1. When it goes from south to north, we call that an ascending path. And when it does that, the look of the satellite, so LOS, let's call it, is going to be toward X. When it goes from north to south, it's what we call descending. And then during this one, LOS is going to be toward west. So we have overall 2 measurements. They are not horizontal. They are not vertical. They are going to be along the look of the satellite or along LOS. But then from this image, you can see 1 for ascending, 1 for descending. When we have these 2 simple math, we can easily get what we need, vertical and horizontal deformations. There are different types of SAR, let's call them SAR satellites that you can use, and they come with different frequency lengths. We have frequency ranges. We have mainly X-band, C-band, and L-band, and the difference is in the lengths of the wave that they send, the wavelengths. X-band has the shortest wavelengths. It sends small objects, but is highly affected by the vegetation, as you can see on the figure. As we go to L-band, L-band has the highest, the longest wavelengths, and then the penetration depth for these types of wave is very good. It passes through the vegetation, minimum effect. And then we have C-band, which is something in between. It provides a good measurement, but still affected by some vegetation. So we need to do some sort of calibration and noise canceling to make sure that the data is accurate enough. Here is a table showing the resolution of different SAR satellites. You can see they change from sub-meter, like for owls, which is 1 to 3, to tens of meters, like Sentinel-1 or NISAR. When you have higher resolution satellites, it provides more spatial details, but then the spatial coverage, you kind of sacrifice it. When we have a lower resolution, it gives us a better spatial coverage, but then you kind of sacrifice the spatial details. So it's kind of a trade-off that you do here, spatial coverage versus liability. And depending on the project, on the application, you can decide which one to go. And the other one, which kind of was important for us, is how to access the data, if they are free or if they are commercially available. Free, right? Commercially, they're very expensive. Each image is going to cost you about a couple of thousand sometimes, depending on the satellite that you use. Our focus in this study was on the free access satellites. Mainly at the beginning, Sentinel-1, because this was the only satellite available from that category. At the beginning, they are C-band satellites. They have a 12-day revisit period. There are always, at least 2 satellites of this type in orbiting the Earth. So it means that we're going to have almost 6 days revisit time for this satellite. And then the resolution comes, with different resolution. They have native, I'll explain it, all the way to high to lower resolution depending on the application. We have NISAR recently launched. It was supposed to launch 3 years ago, but for some reason they delayed it. But finally this summer they launched it. It has a L-band, which is great for vegetated area. It has a period, revisit period of about 12 to 14 days. And the resolution is about 10 meters, which is going to be something great for projects related to geotechnical asset management. And then we also were able to secure access to ALOS data through a proposal we submitted to JAXA, the Japanese satellite system. They have usually this every 5 years in case you guys want to go. I think the next cycle is going to be in 2-3 years. And they provide about 200 images. This one, the images, number of images, not too much to do continuous monitoring, but provide us with some tools for calibration and validation. For Sentinel-1, it was the primary satellite for us for analysis. As I said, there are different types of resolution depending on what you're going to do. You can choose one of any of these. We have native resolution, which for each pixel is about 14 to 2 meters. We have then resample, which is going to be, in case you're going to go for larger areas. Those pixels are going to be very small and then a little bit noisy. When we do resample, we're going to use more of those smaller pixels, 1 pixel, kind of improving the coverage. And then finally, you can also do multi-looking, which is pretty much like averaging over multiple of these pixels. And then with that one, you can improve accuracy for your measurements. And you can see how the size of these pixels are compared to the highways for one of the highways that we did for our study. There are different online or offline platform that you can use for inSAR analysis. The one that we used was a platform called PyGMT-SAR that uses PS, persistent scatter time series analysis. So I'm not going to go into detail with this one, but depending on the type you use, you're going to get different answers, different time series. So just be careful about your choice of, the framework or the processing system you use for your analysis. We chose 2 sites to evaluate the performance of this technology for geotechnical asset management. Was one in Alabama, was one in Minnesota. The Alabama was along US Highway US 231, close to Lake in the Spring. And we had a landslide there that happened in 2019, 2020. And that was the reason we chose this special site. Here on the left, you can see the inSAR velocity maps, and then on the right side, you can see the displacement time series you can get from the satellite. We chose 5 different places to make sure that we see all sorts of deformation. You can see P2 has the highest rate of deformation. P3 also has some, but the others do not move much, kind of, telling us that we were able to capture all sorts of deformation patterns in the area. Something that is cool about this technology, as you can see this image, this is where we had the major failure, 2020. But then you can see with the satellite, we were able to capture, let's call this the failure zone, starting in 2019. So if you had this data, you can imagine with this data, you were able to do some measures. You had this much of time to come up with a solution to prevent this. But since they didn't have it, that failure happened. Here you can see also, one thing cool about this, you can travel down with this path. Like this data is available since 2016, so you can go and check the formation pattern with your environmental factors. Here we have moisture, and then we have rainfall, and you can see most of these deformation, at least for this side, are environmental driven. Anytime we have like the major failure started when we had highest, some sort of, we had a wet season where the soil moisture, the red one, was the highest. It came down during the when the wet season was over. It slowed down a little bit, as you can see. But as soon as the wet season started, the formation happened again, and then the major failure that happened when we had the highest soil moisture. We also compared our data with inclinometer data for validation check, and you can see Pattern wise, we were able to get the exact pattern. The blue one is in clinometer, the black one is, sorry, the blue one is in InSAR, the black one is in clinometer. We were able to capture the pattern. The values, the numbers are different. And the reason for that, as I said, the clinometer provides horizontal deformation. InSAR provides LOS deformation. So that's the reason for different numbers. Still, the patterns show us good value, very, very promising results. And then that's what we use, at least, if you're going to go for some sort of alert system or some sort of management decisions. We also did it for an area in Minnesota, Climax, due to some historic deformation happened in the region. This is still preliminary data for this one. We chose 3 locations since we had data for it. We call them south lower, south upper, and then we had north. This is the time series analysis that we performed from 2017 to 2025. But here you can see how InSAR compares with the inclinometer data in the field. This is for south lower, this is for south upper. For south lower, we were able to capture the trend, as you can see. For south upper, we were able to capture the exact trend. So this got better than that. For the upper part, you can see we have some sort of seasonality in the measurement that I assume is more like, it needs more retuning to make sure that we have the proper values. But still, pattern-wise, we were able to capture the pattern observed in the site. And then here you can see the environmental factors. Again, you can compare them easily because we have the whole values for us. We have, for the environmental factor, we have soil moisture, we have precipitation, and then we have river depth and gauge measurements. And as you can see, all this deformation happened when we had the highest height in the river. When it stops, the formation slowed down. And then when it got, again, soil moisture got a little bit high because of the rainfall happening, we had some sort of deformation. And then anytime we had soil moisture increase, the formation happened in higher strength. So based on this, we concluded that, okay, this is a promising technology. Still needs work because, we cannot control the technology. There are many satellites already there. There are new satellites going and they're going to improve this technology. At this point, it's like, we are in the robotic technology thing, like 10 years ago when we had only hands, moving like, ping pong balls around. But now you saw what happened in the Chinese New Year festival, robotics doing Jackie Chan thing, in the festival. And then, there are always, especially when you use Sentinel-1, we have some limitations because of the vegetation in areas, especially Minnesota, Alabama. There is huge dense vegetation, and that makes, signal clarity a little bit difficult. So for that one, we have a technology called corner reflectors that you have seen in the picture, and you can see one of the examples here that we are here actually to install it for the project that we have for Monroe. They are easy to install. We designed, something very simple installation system for it, so you can install it with like 1-2 manpower easily in the site. And then what they do is significant. Here, this is a project, installation we did for an Alabama project, the Alabama project. We have it in the site. This is the image we got from satellites before installing the corner reflectors. This is the image we got after corner reflectors. Nothing since before that. After installing, 2 things happened. Black became sharp white, means better quality. No pixel becomes multiple pixels. So it increased visibility and increased the number of pixels that could be used easily to improve the reliability of this technology. And how it works, if you imagine this is a satellite and this is the corner reflectors, you just have to make sure that these two look at each other properly. It's like, love at the first sight. So when they have that, then it's going to easily, they make the connection and then they give you the proper image that you can stand, for lifetime. Similar to many relationships. And then I would like to thank you all for having me. Again, thanks to the NRRA, for MnDOT for supporting this project, for ALDOT, actually, for sure. And if there is any question, please go ahead. Again, we're going to be here today. My students are going to have posters, and we will be happy to discuss any questions you have further if needed.
Thank you, Ali. Next, we have Mehdi. We have questions after for the break. Next, we have a dear friend here, Mehdi, summarizing lessons learned from a project that we just completed, sponsored by NRRA, on the use of Wicking geotextiles for building better pavement foundations. Go in alignment with the strategic goal for Federal Highway to try to build 100-year foundations. Sorry, you have very little time, Mehdi.
Yeah, I'll try. Hello, everyone. I'm Mehdi. I'm a PhD student at Michigan State University, working with Dr. Bora Cetin. So today I'll be talking about our project performance evaluation of Wicking geotextiles for improving the range and stiffness of road foundation. So today I would like to focus on lessons learned, like Raul mentioned. So I'll skip some parts briefly. If you would like to see more information, the final report will be available on the website soon. And this project was led by Dr. Bora Cetin and Dr. Popal and Dr. White as co-PIs. And also our technical liaison was Raul Velasquez, Dr. Raul Velasquez from INDAT. He helped us a lot to improve the quality of this project. And I should also acknowledge my teammates from Michigan State University, Dr. Naqvi, Dr. Sadeghi, and from Texas A&M, Dr. Biswas and Avinash, and thank you for their contribution to this project. And I also would like to acknowledge the TAP members of this project for their valuable feedback and help throughout the 3 years of the project timeline. So today I'll start with the introduction, then briefly talk about the methodology that we followed, and I will share some results, and we will wrap up with the conclusions and recommendations. And here is the problem that you see, actually. I hope you're gonna like my AI-generated images on the left. So in cold regions, when temperatures drop, the water starts migrating upward, and that water freezes within the soil foundation. That frozen water expands up to 9% in volume and causing a lot of problems, either frost heave or frost-induced settlement, depending on the pressure coming from the top. So, but this is just half of the story, actually. Then when this frozen water melts in spring, the soil foundation, actually pavement foundation, experience significant increase in moisture, and that increase in moisture causes a lot of distresses, like different types of distresses, like potholes, cracks, rotting, as you can see on the picture in the bottom left. Agencies have to apply some spring load restrictions, and this costs a lot of money. So that's the problem here. So what can we do about this? So first of all, to answer that, we have to know the mechanism of frost heave, and to have these are the conditions for frost heave. So you have to have freezing temperatures, frost susceptible soil, and water supply at the same time. Of course, we cannot change the weather conditions, and replacing soils is also not practical all the time. But the most realistic target here is the water supply. We can play with the water, and that's where Wicking geotextile comes in, actually. It has standard properties of the geotextiles, but it also adding some benefits like moisture management and drainage. These Wicking warps are drawing water into the fabric and then pulling them out to the pulling them out to the shoulder, towards the shoulder, and it is providing moisture management, uniform distribution, and also better efficiency in drainage. So here's the goal. Actually, today I'm just talking about the field part of this project. My colleagues already conducted multiple large-scale tests in our laboratories in Michigan State University, Texas A&M, and INGEOS. So this is the goal. So we also wanted to see the performance of this geotextile in Minrod facility. And here are the test locations, 250 feet wide, and sorry, 250 feet long and 39 feet wide, two test sections. They're identical, as you can see here. Sorry for this noisy slide, but I had to show all the instrumentation that we had here. Moisture sensors, suction sensors, shape array accelerometer for deformation in different offsets and in different depths for base, sub-base, and subgrade layer here. The only difference between these two sections is that blue line, which is Wicking Geotextile, placed at the interface of the sub-base and subgrade. So before I talk about the monitoring results, this is the most critical part of this project, actually. Unfortunately, we had some construction-related issues, quality-related issues during construction. So this is the as-built condition of sub-base material for control on top and for Wicking Geotextile. So you see blue means, of course, the better quality. So after the compaction, we had 37% lower stiffness in Wicking Geotextile section because of some schedule constraints during construction. So we had to place the other layers on top of it. So this is the intelligent compaction result for sub-base. Similar trend for base with 23% lower stiffness. So, okay, the Wicking Geotextile section started with lower stiffness, I mean, with disadvantage at day first, but it also gave us a chance to see the performance of this Wicking Geotextile under unfavorable conditions. So, which was great thing for us at the end of the day, by the way. So, when it comes to the monitoring results, I'd like to talk about the moisture content first. I will share just two different moisture sensor results for today. First one is from subgrade at 33 inches depth, which is 3 inches below the geotextile. And this red line is for control and the blue one is for Wicking Geotextile. I think everything is so clear here. The difference is super clear. And also during spring thaw, right after that blue shaded freezing season, the increase in control section in moisture is significantly higher than the Wicking Geotextile section. It was drier, but at the same time, it provided us uniform moisture distribution throughout the section, which is really good. Studies, there are multiple studies out there, but studies show that just 2% increase in moisture can significantly increase the permanent deformation or decrease the MR result modulus. So this is really critical for us. And this one is sub-base sensor. So the difference is not that significant in terms of the amplitude of the moisture content, but if you check the spikes after each rainfall, you see at this side of the slide, control section had significant fluctuations after each rainfall, but Wicking Geotextile provided uniform moisture, and it was even drier in some periods at sub-base. So this is above the geotextile, by the way. And just one example from the displacement profile from the inner wheel path of the passing lane. This is our shape array sensor. And in this project, actually, we mostly see this in different projects. We are still working on this to understand the shape array sensors, but the existing interpretation is like right now, we think that we have frost-induced settlement because of the surcharge pressure and flexure restraint coming from the top thick pavement. So we had higher settlement in control section near the center line of the road. And Wicking Geotextile was almost stable compared to the control section here, especially in 2024 with milder winter. And in addition to these sensor results, thanks to Minrod team, especially Jacob, he conducted multiple FWD tests in different seasons and months to see the structural performance of these test cells to be able to understand the performance of the geotextile. So, of course, we did back calculation with these test results, but back calculation has some flaws and it doesn't allow us to do apple-to-apple comparison. That's why we wanted to go with the deflection ball parameters recommended by FHWA 2017. This first index is base layer index, which represents the performance of base layer, mostly base layer, depending on the depth of the layer. We have 14 different FW test results throughout the project period here. So first of all, again, it provided uniformity. Coefficient of variation of Wicking Geotextile section was 32% lower than the control. And also Wicking section had a higher BLI, which is bad actually at the beginning of the project. But right now, if you check the last test results, they're almost identical right now. So if you check the long-term performance of the Geotextile, they are converging to each other, which is a good thing, but still 3 years of period of time is, I mean, we don't identify it as long-term actually. To see more significant benefit from the Geotextile, actually we should observe and monitor these sites for more years. And the second one is MLI, middle layer index, which represents the performance of sub-base. The trend was similar here. And the last one is lower layer index for subgrade. The difference was, the gap was narrower compared to the other ones here, but we observed a similar trend here too. So these are the conclusions. I don't know how much time, just 3 minutes? Okay. So the first one is, again, as I mentioned, we initially had 12 to 45% lower stiffness across layers in Wicking Geotextile section. But even with this disadvantage, we had effective drainage with functional outlet. I'll mention this functional outlet thing in lessons learned section. And we had more uniform moisture distribution, reduced frost-induced settlement, and as I said, stiffness gradually converged with control section by 2025. But again, we should monitor these sites for more years to see more significant differences between these two sections. These are the lessons learned, 3 lessons learned here. So first one is the proper compaction, which is really critical for the structural performance, but at the same time, for capillary continuity, we need proper compaction to have that contact between the soil and sub-base, or depending on type of soil, and geotextile, which is really critical because if you don't have capillary continuity, unfortunately, this geotextile doesn't work properly. The second one is the functional outlet. Actually, in the report, it's clear, but I didn't have time to elaborate on this today. So we observed some differences between the driving lane and passing lane. So the pictures that we had from the field showed that we had some problems with the drainage outlet at that site. So that's why it didn't give us good results compared to driving lane. So this is the cross-section provided and recommended by the manufacturer. Can I give the name of the manufacturer? Okay. And this is the daylighting option. So we are recommending this option because this ditch design is really tricky and it requires proper quality control, especially at the termination of the geotextile. So you see some water accumulation over there. It's really critical. And the last one, the quality construction and inspection at terminations. If we have a ditch design, even with the daylighting design, because the main concept here is the suction gradient. That side of geotextile, the termination of geotextile has to be drier than the inside. Otherwise, if you are on the wet side on shoulder, unfortunately, this is even leaking the water inside the system. So this is really critical. So thanks to the NRRA for the continued support, for their feedbacks and support. Special thanks to Solmax for providing this geotextile for this project. And of course, thanks to Raul and Jacob for their help for this project. And of course, the Minro team for their help during the construction. Thank you very much.
Thank you, Mehdi. Any questions? He got a poster out there. You can agree with him during the okay. Yeah. Next one, before the break, we have another emerging topic, another trending topic in the geotechnical community, which is the measuring while drilling. And we have NRRA project. And Professor Sadeghi, aka Mo, has been becoming one of the leaders in implementing and using this technology. And you're the lead now on the working group for DFI, Deep Foundation is in Informational Weathering, right? So,
Yeah.
So anyway, for further ado, Mo, take it away. So you have about 15 minutes.
That's all right. Thanks. Yeah, so this project is about measurement while drilling, which is in line with what Silas was talking about. It's an attempt to improve the site investigation, geotechnical engineering. So the project was to instrumentation and data management and analysis of the data. So last year I talked about the instrumentation and data management. Today I'm just going to focus mostly on the analysis of the data. So, but a little bit, if you are not familiar with this technology, so measuring while drilling, basically we install some sensors on the drill rig. And then, so there are four sensors to measure four parameters, rotation, speed, penetration rate, thrust, and torque are the four parameters that are collected for all drilling types. But if you are doing mud ordering, you collect two additional parameters, which is the mud injection pressure and mud flow rate. So these six parameters now we're going to use to enhance site investigation. There are so many different things that we could do, or we hope that we can do with this. But the ones that I wanted to focus on for this project was first to classify the soil based on these data. Well, obviously you might ask, well, you're drilling, you can see the soil. That is correct. So you could classify the soil based on that. But the accuracy of that is like up to 1 to 2 feet. So hopefully if this works, we could actually get the transition from one layer to another layer with a lot more accuracy. After that, we want to develop correlations between these parameters that we're collecting during the drilling to the soil properties of interest, CPT, SPT, undrained strengths of soils, and even UCS of rocks. So after instrumentation, we collected a lot of data. We drilled 36 boreholes. 26 of them were drilled using HSA, hollow stem auger drilling. The other 10 were mud rotary. So we collected, we collected the measurement while drilling data. We did some in situ testing. We collected some samples and did the lab test. So now we wanted to see what we can do from this collected data. Well, first, again, these are the 6 parameters that we collect for all types of drilling, and the last 2 only for mud rotary. So these are what we call individual parameters. Then there are a bunch of equations that most of them are physics-based, but some of them have some portions are entirely empirical. So these are compound parameters. These are some equations that calculate some properties from these individual parameters. So we have 6 individual parameters and a lot of compound parameters. These 8 or 9 are the most commonly used and beneficial compound parameters. So we're going to use these to develop correlations and also soil classification. So the first one that we did, we were trying to classify the soil. So we plotted all these combinations, the combination of all 6 individual parameters with the compound parameters, a lot of pictures. Then we first plotted them color-coded based on USCS or Unified Soil Classification Systems. Was a lot of scatter. Then we simplified the classifications based on this. So anything CL, CLML, topsoil, CH, we call them clay, MHML, silt, and so on and so forth. So this was the best separation of the data that we could get from this. So again, you can see there's a lot of overlap. But a lot of this overlap are actually can explain. But overall, I was able to divide this plot to 4 distinct areas. Area 1 is mostly occupied by sands, silty sands, and sandy silts. 2 is more gravel area. 3 is more silty, and 4 is clay. Well, this is just my initial attempt, so it's especially I don't like this little corner. We don't have in nature some sharp changes from one layer to another layer, but this is the first attempt, right? So more data, if more data becomes available, hopefully we could improve on this. But this actually works. I have done a lot of comparison between this because we also have some CPT data. We use the CPT data. We'll talk about it in a minute. compare them, and they are in relatively good agreement. So I think it's not a final classification, but it shows that we can get somewhere with this data. The next one that we wanted to do to compare CPT and measurement while drilling data, the first attempt was just plot them on one plot. The scales are so different that the measurement while drilling just becomes a line. We cannot compare them, so I normalized them based on this equation. And now we could actually compare at least the trends, if there is any correlation or there's any hope of correlation. So doing that, as you can see, there is actually really good correlation. So we should be able to predict one from the other. So in this case, we're measuring the NWD data, and we want to predict the CPT, right? So a lot of our data, some of our data actually showed really nice trends, similar trends, which was encouraging. But then we came across some plots like this that you can see it's all over the place. So we have 8 CPT data that we have measurement while drilling right next to it. And all of those measurement while drilling were HSA. And we realized during this project for the first time that actually there is a specific issue that occurs when you're drilling with HSA. And that's this issue. Sometimes when you're drilling in high plasticity clay, and it's not a traditional explanation of high plasticity. If your liquid limit is above 30-ish, and your plasticity index is about above 15 to 20, you'll see this phenomenon. So each one of these lines are one flight of auger. At the beginning of the auger, the torque is normal, the thrust is normal, but as you go down with that single auger flight, the torque increases and the thrust goes down, and actually sometimes it gets to negative number. That tells us that something's wrong here. We did a lot of investigation on this, and we realized that when we have high plastic clay, it sticks to the auger and it kind of clogs the drill rig, so it increases the friction as it goes down. So the torque goes up, and then it creates a corkscrew effect kind of, and the thrust goes negative. And then at the end of the flight of auger, when they stop to add the next one, they actually sometimes drill, not sometimes, almost all the time, drills for a few minutes to get the cuttings out. So it clears out the borehole for the next run. So it starts again normal, and the same issue happens. So, so I wanted to see if we could actually still work with this data, because at least the first few inches of every auger should be fine. After that is when the auger becomes clogged, and then the issue happens. So what I did was I took a first half foot of each auger flight and took the average and replaced the whole section with just that average, right? It's not perfect. I just wanted to see this very oversimplified method. I just wanted to see if I could find that same trend with this. And actually it turns out that now, if I do that, there is the same problem that I had. Now the trends are matching a little bit. Not perfectly, obviously, but it works pretty nicely. So then, because again, that's oversimplified, because when your torque goes up, thrust goes down, it's not just that you could fix those. Those two parameters are affecting everything else, the rotation speed, the penetration rate, everything. So I want to see if I could use machine learning with all the information data and then some, like for example, if I'm above the groundwater table or below the groundwater table, and see if I could get some meaningful data from this erroneous initial measurement while drilling data, so to speak. And it turned out that actually I can. So if I did this and then used some of the data that the developed model have not seen, try to predict the data, and then I had the actual data, I plotted them, and as you can see, I could get some decent trends. And then some of those same problems, I had one of the formulas that we did not see. We had to see CPT. I plotted that against the CPT predicted by the machine learning model from measurement while drilling data. As you can see, they match very well. You obviously have some issues that we cannot predict the negative pore pressure just yet, but we're working on that. So then also, again, as I mentioned, I use the CPT because from CPT, you could classify the soil as well. I classified the soils from the CPT data, but on the same plot that I have developed these 4 regions. Obviously, it's zoomed in, so I could look at it. And again, there is a good correlation. There's a lot of scatter, but all of those scatter are explainable, right? The only thing that I noticed is that little corner at the bottom of the plot is where all the soils that are classified as sensitive by CPT are all on this little corner here in the red crosses. So I added that one little section to my plot. So this is one plot that I have for now. It's not perfect, but that could be used for soil classification based on measuring while drilling. I just want to emphasize that you don't like this corner, but I will work on that later on. All right. So again, optimization of another thing that you could use measuring while drilling data is to optimize your drilling process. That was not part of the scope of this project, but because of all that issue that we saw with HSA, we said, well, let's use that and optimize the HSA at least. So we went on site, we did 5 new boreholes, tested various differential penetration rate and rotation speed, and plotted them against the specific energy, which is the representation of how much energy you would use to extract a volume of geomaterial. And as you can see, if your penetration rate to rotation speed ratio is on this area, you have a higher energy. As you enter this area here, you have the minimum, and if you move on again and increase the ratio, the speed again starts to increase. We found the bottom, the lower boundary to be about 0.05 foot per rotation. We didn't have enough data to find a clear-cut upper bound, but it should be conservatively about 0.8, 0.9, or up to 0.1 foot per rotation. Then, during that same optimization, we tried to see if we could actually overcome that issue of increasing torque with that. So this is an example. So these are 2 boreholes that are drilled about a foot and a half away from each other, next to each other. So this section here, as you can see, the torque is increased again. This is not as sharp as we would want it to see because the clay cycle was not as plastic, but we can still see some increase. Then what we did is by reducing the penetration rate, everything else the same, reducing the penetration rate, as you can see, the increasing torque decreases significantly. And even if you lower penetration rate and rotation speed at the same time, the increase actually is improved even better. So that was a suggestion that we came up with to address that issue. So the next thing that what we did was we want to predict SPTN values from measuring while drilling data. So one of the questions, all of these tests that we did the measuring while drilling and the in situ test in the same borehole. So when you do that, the problem is if you did this SPT here, so this soil here is, so you drill up to this point, you do the SPT test in situ here, and this soil is highly disturbed, and there's a hole at the middle after you're done with the test. Then you take the sampler out and then drill over it. So the measurement while drilling that you collect over this area is from a disturbed section. We want to see, can we use that section, average the measurement while drilling for prediction, or do we have to use the interval after or before? We also use, because in SPT, we drive the sampler 18 inches, but we ignore the first 6 inch. So we want to see if we average over the entire 18.6 in the 3 intervals, or just the 12 inch that we actually consider which one works better. We actually find out that the same depth, despite the disturbance, if you use the 12 inch interval, gives you the best results. We actually look at the measurement while drillings for the intervals before and after to see if that disturbance actually has some effects on the samples. For pretty much all the soils, there's almost no effect except for clays. The clays do have some effect. So the signatures here are different from those areas, but clays in general have so many noises in them anyways, right? So overall, the best results are going to still be from the same distance. And so this is the correlation that we developed. R squared of 0.6, not very impressive, but for geotechnical engineering, I guess that's okay, right? So, but again, then I developed machine learning models for them. Again, optional networks use 9 input parameters this time, because compound parameters do not take into account these two, right? So we took them into account as well, and we separated them if they're above the groundwater and below the groundwater, because that has effects on both SPT and measurable drilling. The correlations look perfect when you do this, but it's actually not as perfect as you would think. So then I had to develop a model and try to develop a continuous SPT value for each borehole. And the red ones are the actual ones. So the black one is with the linear regression simply, but with some one compound parameter correlation. And this one is the blue one is the artificial neural network, which had the R squared of 0.9. So when it comes to higher SPTM values, actually measurable drilling does a better job. For the lower ones, especially this story, I picked this borehole specifically because this is one of the worst comparisons between ANN and SPT N values. I picked this on purpose because it shows a very important flaw of measurable machine learning models if you don't have enough data. So as you can see, these two areas, actually the linear regression works a lot better because these two areas are actually gravel, right? But they're very loose gravel. They have very small, very low SPTN value, right? So two problems. Usually the gravel, because of the gravel nature of the soil, it still changes the signature of measurement by drilling. But if it's still loose, your SPTN values are going to be very low, but because of those change of the signatures, because of the large grains, the predictions are going to be much higher than the actual SPT, right? So that's one of the drawbacks of this method. However, I have to emphasize that our data was not uniformly distributed, so we had very little gravel samples in our data. So on all the gravel samples that we had either were at refusals or very low SPT, right? So we need more data, but for now, it works. Then we did the same thing for under shear strengths. One thing that I have to emphasize here for under shear strengths is we could measure the under shear strength in 2 methods, unconfined compression strength or triaxial UU test. We could not develop any correlations for unconfined compression strength testing, simply because those samples are collected from the lab, from the field and tested. The moisture content on those samples are so different. The range was from the samples that we tested was from 20% to 89%, 90%, the moisture content. If you have the same soil with that range of moisture content, the strengths are going to be all over the place. However, when you do UU, because it's a triaxial test, you actually saturate your sample first and then test them. Then your data becomes a lot more uniform. So you could develop, you could predict the under shear strengths under UU test. Again, I did machine learning, seems perfect, but this is the actual drawback of how it does not work. So in this case, I took 20% of the samples out. The machine had not seen them. I trained the model and then gave them measurable drilling data to that trained model and asked them to predict it. Then I plotted them. As you can see, R squared is 0.9. It's almost perfect, right? But then again, I kept one bore log out and tried to estimate that with the trained model. And as you can see, the model is simply memorizing where I have data.
everywhere else, it's just predicting a weighted average, okay? And I have an explanation, we don't have time, but I have a really good explanation why this machine learning models work for some cases, not for these cases. If you want, I'd be more than happy to discuss this afterwards. I just wanted to emphasize that plots like this for measurement reliability, for machine learning are not reliable. You have to always check going deeper into your classifications. And the last thing is UCS, we just didn't have enough data to predict the UCS of rocks. So that's all we have. Thank you.
Thank you, Mo.